Problem F716. Draw the shear and moment diagrams for the beam. So in this beam we have two reactions at A and at B, and two distributed forces here and here. So first we're going to need to find these reaction forces. We'll do that by finding sum of force and sum of moment. Sum of force, we have this 6 kilonewton per meter distributed force downward here, this 6 kilonewton per meter distributed downward force here. Upward reactions at A and B, set them all equal to 0. After we evaluate these integrals and combine like terms, that gives us the equation Ra plus Rb minus 18 kilonewtons equals 0. For the moment, we are going to pick a point. Now, you could possibly get away with picking this point or this point, either point A or point B, but in the spirit of making things consistent, I am going to pick the leftmost point to be x equals 0. So that gives us the integral of w times x dx, the reaction at A, reaction at B, and another integral of w of x dx. Put those together and you get this formula right here. Solving our two Newton's second law equations, we get that the reaction at A is 9 kilonewtons and the reaction at B is 9 kilonewtons. Now if we look at this problem, we see that it actually is pretty symmetric, with the sole exception that B is a pin support and A is a roller support, but that doesn't matter with the current loading because there are no horizontal forces. So we actually would expect a lot of symmetry out of this problem. Now we could utilize this symmetry to make this problem easier, but I'm going to do it the hard way to show you how it can be done. So next we want to find the shear function. Now there is a force over here at the leftmost point, but it's a distributed force. There is no point force at the leftmost point, so the shear starts at 0. Furthermore, we can break this beam up into 3 sections. This section right here, this section in the middle, and this section right here. For the leftmost section, we have shear of x is equal to shear of where it starts, plus the integral from 0 to x of the w function. Integrate that, evaluate it, and we get that the shear function is equal to negative 6 kilonewton meters x, from 0 to 1.5 meters. Now we could, for our next segment, plug in 1.5 meters into x and get that shear is equal to 9 kilonewtons. However, this reaction force at A represents a point force, which means that the shear function will be discontinuous at x equals 1.5 meters. So what we have just found is, in mathematical terms, the limit as x approaches 1.5 meters from the bottom, which I've indicated by writing it like this. V of 1.5 meters with a negative subscript, meaning that we're approaching 1.5 meters from below 1.5 meters. And that indeed is negative 9 kilonewtons. But because there is this sudden applied force from the reaction at A, which is equal to 9 kilonewtons, the shear as the limit approaches 1.5 meters from above is the shear as it approaches 1.5 meters from below plus the 9 kilonewtons, which nicely brings it up to 0. Now for the second segment, there is no applied force, which means shear is constant, and shear is 0. So for all of this region, shear is 0. Moving into this third region, we do again have a discontinuous shear function because we have a point force from the reaction at B. So once again, we need to say that the shear as x approaches 4.5 meters from below is 0, plus that applied force becomes the shear as x approaches 4.5 meters from above. So going into this last segment, the shear of x is starting at 4.5 meters, which is this 9 kilonewtons, plus the integral from 4.5 meters to x of our w function. Integrate that, evaluate it, and you get this is our shear function for that region. Moment. We look, there is no applied moment at the leftmost point, so moment of 0 is equal to 0. To find the moment in the first region, we take the moment at 0 and integrate the shear function, and that gives us this formula right here. Now for shear, there was an applied force, which means we had a discontinuous jump in the shear function. But there's not an applied moment, so there is no discontinuous jump in the moment function. So we can once again use moment of 1.5 meters by plugging 1.5 meters into here. And that is the start for the second segment. Now this segment is a bit easier because the shear function is 0, integral of 0 is 0, which means that the moment in that middle part of the beam is a constant negative 6.75 kilonewton meters, which means also moment at the rightmost point of that segment is negative 6.75 kilonewton meters. Then for the last segment, we say that the moment of that region is equal to the moment at the start of that region, plus the integral from the beginning of the region to x of the shear function, which, remember, the shear function we calculated was this. The integral of that shear function, we can first do the indefinite integral, so 36 kilonewtons becomes 36 kilonewtons x, and negative 6 kilonewtons per meter x becomes negative 3 kilonewtons per meter x squared. X to the first becomes x to the second, and then we divide by this 2. And so we get that the moment function for the second part of for that last bit of the beam is given by this formula right here. Now graph it. How will we graph this? Well, for the shear function, we see that shear goes up in a up continuously. Then it jumps down to 0 at 1.5 meters, or jumps up to 0 rather, because it's going down. Sorry, it's going down in a linear manner. Jumps up to 0, and then jumps up again to 9, where it will then go down at a continuous rate. And as a side note, if there's no force on the leftmost point of the beam, that shear is 0. Same is true for the right. If there's no force or no moment on the rightmost part of the beam, then the internal shear and internal moment respectively should each be 0. So 2 discontinuous linear sections with a 0 in between. It looks like this. Now for the moment graph, we could hand wave it. We could say that moment, because again there are no applied moments on this side, there's no applied moments on this side, that it should start and end at 0. Furthermore, from looking at the shear graph, we see that it should start at 0 and also with a 0 slope. It should curve upward, or in this case downward, and then it should stop. It should be steady for a while, and then it should curve upward, slowing down to getting to 0, and that's what we see here. Or once again, we could use our preferred spreadsheet program, find x, v of x, and m of x, making sure to put in a double value for x at our discontinuous points, so at 1.5 meters and 4.5 meters. Plug in our shear functions for a separate shear function for each of those regions, and a moment function, again a separate moment function for each of those regions.